Modern education often assumes that interactive, dynamic media and collaborative social learning inherently produce better outcomes than static text and solo study. Yet, controlled empirical research often proves this assumption wrong. In many scenarios, reading static text significantly outperforms listening to audio narration, a phenomenon known as the reverse modality effect. This chart displays the results of an A/B test comparing learning formats. The left bar represents students learning from smooth, continuous animations. The right bar, which is significantly higher, represents students who learned from static, unmoving graphics. The physical constraints of human cognitive architecture render these failures predictable. Designing effective instruction requires treating media as an engineering problem governed by two specific mechanisms: the transient information effect and the collective working memory effect. The transient information effect occurs when vital information disappears before a learner can adequately process it and link it to incoming data. Speech and continuous animation are transient by nature. If it is not recorded or written down, the information dissipates instantly. The critical variable determining whether this transience is harmful is element interactivity, the inherent complexity of the information being presented. Transient information disrupts learning only when the content is complex enough to require the brain to hold and manipulate multiple variables simultaneously. This diagram illustrates working memory as a severely constrained biological bottleneck. When information is permanent, like written text, it stays stable within the buffer. When transient data enters, it demands massive processing space and evaporates before connecting to new inputs, triggering a system overload. Researchers Leahy and Sweller demonstrated this by testing students reading temperature time graphs using identical information delivered in two different formats. When given long, complex explanations via spoken audio, learners failed because their working memory overflowed, trying to hold earlier sentences while processing the visual graph. When the exact same text was written down, learners succeeded because they could skim, pause, and offload their memory to the physical page. Written information acts as an external hard drive for the brain, neutralizing the complexity of high-element tasks by allowing the learner to control the pace. This vulnerability extends to visual media. An animation is effectively a rapid sequence of transient images. To understand frame 50 of a moving mechanism, the learner's brain must actively hold and integrate frames 1 through 49 in working memory. Static diagrams force the learner to mentally integrate the steps themselves, which results in deeper, more active cognitive processing than passively watching a continuous video. This timeline models a cognitive load meter during video playback. Granting the learner control to pause and play the animation prevents working memory overflow. Segmenting is the second fix. Chopping a complex animation into distinct chunks reduces the volume of transient data held at one moment. These mitigations are unnecessary for experts. Due to the expertise reversal effect, an expert's existing mental schemas automatically compress incoming data, making segmenting redundant. For novices, animations are a cognitive hazard because they force the brain to battle both the inherent difficulty of the subject and the fleeting nature of time simultaneously. There is one major exception. Continuous animations consistently outperform static graphics when teaching human perceptual motor tasks. Empirical tests confirm this superiority in physical tasks like knot tying, origami, and the specific hand and body manipulations required for first aid. This occurs because imitating human movement is classified as biologically primary knowledge. Biologically primary knowledge consists of skills humans have evolved to absorb effortlessly, simply by watching others. The physiological mechanism driving this efficiency is the mirror neuron system in the human brain. Mirror neurons allow us to bypass standard working memory bottlenecks by mapping observed human movement directly onto our own motor cortex. This differs from mechanical or abstract systems, representing biologically secondary knowledge, concepts we haven't evolved to learn natively, requiring immense cognitive effort to process. If the subject involves human hands moving through space, dynamic animation is the optimal delivery method. If it involves abstract data or gears turning, animation is a liability. Moving beyond how information is presented to consider who is processing it leads to the study of collaborative learning. This requires evaluating group work purely as a biological offloading mechanism rather than a social exercise. This diagram illustrates the collective working memory effect. A group of learners operates as a single, expanded information processing network. When tackling a complex task alone, individual capacity is quickly overwhelmed. Dividing the intrinsic load across multiple brains allows the group to avoid individual overload. However, there is a hidden tax to group work, known as transaction costs. The act of communicating and coordinating between group members consumes significant working memory overhead. Studies by Kirschner on biological heredity measured the exact mathematical tipping point where collaboration becomes beneficial. Group work fails on low-complexity tasks because the individual already possesses enough bandwidth. Adding communication friction merely wastes cognitive resources. Group work succeeds on high-complexity tasks where individual bandwidth is insufficient. The transaction costs are a necessary price for pooled processing capacity. Collaboration is an emergency processing protocol that should be deployed only when a task exceeds a single brain's limits. This matrix shows design must be governed by strict applicability conditions, not technological novelty. When a task is complex, transient media without segmentation destroys learning. For low-element interactivity tasks, forcing collaboration degrades efficiency via transaction costs. The existence of a tool, whether an animation engine or a collaboration platform, is never a sufficient reason to deploy it. Instructional efficacy is determined by how strictly a design respects the physical bandwidth limits of human cognitive architecture.